Hello, I'm Guillermo Castilla, and this is Aula UE. Today we're going to talk a bit about statistical inference, and to do so, first we're going to introduce the concept of point and interval estimation. So here we have a population, okay, it's that bar on the top with a number of variables, and there you have the mean of the population, which is that mu. Okay, the population by definition is unknown. What we do know about are these. These are samples. Now, why is the population unknown? Well, the population is unknown because we can't actually measure every single element in the population to give a certain known value. So, we use Greek letters to mark when we're talking about the population, just to know that technically they are unknown, or they cannot be found unless we have an anomalous or gigantic number of measurements. Well, we use the Latin alphabet for the known samples, because we do know everything about the samples, because normally we've taken samples up ourselves. So the idea of point estimation is that following a number of variables from a sample, like the means of the sample, we want to get the mean of the population, or we want to get as close to it as we feel comfortable. Okay, we want to be able to make the best possible guess, and that's probably what all this estimation stuff is about. So this is not just about means. This is not just obtaining the mean of a population or the mean of a sample and going from one place to another. We can actually use it for any variable. That's why we usually use the Greek letter theta for any generic population variable. And we use the Latin letter x, as we've been using so far, always, for a generic sample variable. Okay, so if you've got the generic population variable and the generic sample variable, what we call is theta circumflex, the one we've got on top. Okay, theta circumflex will be the estimation of that population variable. So we use sample variables to estimate population variables, but the calculated variable, okay, the theta circumflex, isn't the real theta. It isn't the real population variable, because that one is completely unknown. It's our estimation of it. Okay, it's the best guess we can make towards that variable. So we're going to play along that, and let's see where it takes us. Okay, so let's talk first about estimations in very well known distributions. Okay, in very well known statistical distributions. So what estimations do we have to know distinctly? Well, they are quite straightforward, actually. Most of them you could even guess them, or they would probably be the logical thing you would do. This actually follows two methods. One that's called the method of the moments, or the method of moments, and the other one is called the method of maximum verisimilitude. But they're extremely complex, and they're probably not worth while telling, just for the use we're going to make of them here. So what we're going to do is we're going to estimate the population variables of the mean of a normal, the standard deviation of a normal, the lambda of a Poisson, and the p of a binomial. As you can see, all of them are the mean of the sample, except for the standard deviation of the normal, which would be the standard deviation of the sample. So normal, Poisson, and binomial each we can each estimate the variables of the population, mu, sigma, lambda, and p, through the variables of the sample. Okay, this is, if we don't have anything better, this is the best guess we can actually make. Okay, mu is x, sigma is s, lambda is x, and p is x. Okay. Well, so far so good. This is all about point estimation. Okay, we're estimating where this point is in our population. But of course, we don't only want the certainty of a point, because we're practically sure that it's not going to be exactly that point. It's going to be close by, probably, but not exactly that point. So how can we estimate an interval that gives us a certain certainty? We know that there's a certain amount of uncertainty that our variable can fall outside that interval, and there's a certain amount of certainty that it can fall in the interval. So we're trying to calculate now intervals, okay, that give us a percentage of probability of the population variable actually being inside that interval. So what we're going to try to do now is create confidence intervals. We will call our uncertainty alpha, which is a percentage, it's a probability, it's the probability of it not being in the confidence interval, and 1 minus alpha is the certainty, it's the probability of it being inside the confidence interval. By default, alpha is usually always a 5%, because we want approximately a 95% certainty and a 5% uncertainty. The bigger the certainty, the better. Okay. So we've been talking about known point estimators. Now let's talk about known confidence intervals or interval estimators for known distributions. And we're really going to concentrate on the normal. We'll also see one for the binomial, but the biggie here is the normal. Okay, because we're going to study 3. One for mu, one for sigma, and paradoxically another one for mu. Okay? So how does this go? Well, why do we have 2 mu's first? Because it depends if we know the sigma or if we don't. Okay, how can we know the sigma if I just said they were unknown? It's because if it's only valid if sigma is a given. Okay. We can know certain population variables because we have measurements of that population for a billion results or a large number of elements. So when we know a population variable, it's because it's a given. Okay. So what we're going to do now is we're going to create an interval, I sub alpha. Okay, it's our confidence interval. And when we know sigma, the confidence interval for mu is x plus minus z sub alpha times sigma divided by the root of n. Okay, so I have a 1 minus alpha % chance that my estimated mu is in that interval. Okay. When sigma is unknown, instead of using sigma, of course, we have to use s, okay, which is the sigma, it's the standard deviation for the sample instead of for the population. So when we use s, it changes a bit. So we've got a number of variables there. So far we know x bar, we know is the mean of the sample, sigma is the standard deviation of the population, n is the number of measurements, s sub x and s sub x square are the standard deviation and the variance in the sample. So we've got 3 things there. Well, actually 4 if you take a look, that we don't really control much, which is z sub alpha, epsilon sub 1 alpha, epsilon sub 2 alpha, and t sub alpha. So we're going to see in a minute what that's all about. But let's do this the confidence interval for the binomial that I spoke about before, and see how it goes. I sub alpha for the p of a binomial is actually p plus minus z sub alpha over the root of n times n pq. Okay, I'll have to look into that later on. Very well. Okay, so what are these z sub alpha, epsilon 1 alpha, epsilon 2 alpha, and t sub alpha? And what is this good for? Okay, I want to repeat that these are confidence intervals. Okay, so when I calculate these intervals, I have a 1 minus alpha % chance that the variable I'm looking for, mu in the first case, sigma in the second, mu in the third, and p in the fourth, will belong to that interval. So if I have, for example, a confidence interval for mu in a normal that goes from 1.2 to 1.5, it means I have a 95% chance that the population mu, okay, the mean of the population, is in between those two numbers. So if my point estimator is in between those two numbers, it's quite probable. So Z sub alpha belongs to a normal 0, 1. Epsilon 1 and 2 belong to a chi-square n minus 1, and T sub alpha belong to a T minus n minus 1. So how do we calculate this? This is actually quite simple. All we have to do is we have to take alpha, actually it's not really alpha, it would be alpha halves, okay, and put alpha halves in each side of the distribution, and from there we obtain the Z sub alpha, the abscissa, for that certain percentage. Okay, it's exactly the same thing with the chi-square. Remember, it's chi-square n minus 1, so if we have 20 measurements, it's the chi-square 19, okay, and they have epsilon 1 alpha and epsilon 2 alpha, and if this area is alpha halves on each side, let's just write this as alpha halves so no one gets wrong there. It's alpha halves on each side for epsilon 1 alpha and epsilon 2 alpha. And in the T of students, it's the same thing. So it's just those values, Z sub alpha, epsilon 1 alpha, and epsilon 2 alpha, as long as T sub alpha, are just the abscissas, okay, for my distributions when there is a probability of alpha halves to each side. Okay, the reason that Z sub alpha and T sub alpha only have one value, whilst epsilon has epsilon 1 and epsilon 2, is just a reason that the normal and the T of student distributions are symmetrical, okay, regarding the 0, whilst the chi-square isn't symmetrical, and so we actually have to calculate each variable separately. But usually the chi-square and the T-student tables are very, very easy to use, and we get those values very quickly. The moment we actually know how much alpha is, it's just a mere glance. It's very easy to find. So I hope you found this relatively useful, and I'll see you around here on Aula. See you soon.